Let me figure out how to use this. Is there a this? Maybe I can continue with that point.
This is also a point here. I don't know.
Okay. Yeah. Okay. All right. All right. Thank you so much for having me here. So I'll be basically talking about small-scale cosmic web in the context of reionization. You know, Christoph yesterday told us that the cosmic web can exist in many different scales, and probably the cosmic web I'll be talking about is small sub-megaparsec structure might be the smallest one that gets discussed in this conference. Yeah. So I guess I don't have to talk much about reionization anymore because it was introduced many times, but basically I'm going to show you this movie by my collaborators, the Cosmic Dawn Simulation, where reionization starts as small ionized bubbles around bright galaxies, and it's supposed to play. It doesn't play. Whatever. Yeah. And eventually these bubbles would expand over time to fill the entire universe to complete reionization. So this inhomogeneous reionization pattern has crucial information about the star formation physics we don't fully understand, and also it gets imprinted on various observables like 21 centimeter. Well, the neutral part will emit 21 centimeter emission, and the bright part will emit H alpha, which gets redshifted to near infrared background today, and also the ionized bubble will scatter some of the CMB photons, and while doing that, they will Doppler shift the CMB photons according to their peculiar velocity, so thereby adding some small-scale temperature anisotropy in the CMB, which we call kinetic swing observability effect. Yeah, so we want to be able to model the inhomogeneous reionization for given assumptions about this star formation, the early galaxies, basically ionizing sources of the reionization. And in doing so, naturally, people have been mostly focused on structures, halos above 10 to the 8 solar mass, because that's like the Jeans mass of the ionized gas, and also that's the mass that halos can collisionally excite hydrogen atoms and then radiate away its energy, and therefore cool itself and form stars. But then in this talk, I'm going to show you that during reionization, the neutral part of the IGM had much lower temperature, and therefore it was able to form a lot of small-scale structures, small-scale cosmic web below megaparsec scale. And by doing so, it can increase the recombination rate when the volume gets ionized, and therefore affect the reionization in the large scale. And also in the second part of the talk, I'll talk specifically about mini halos located at the dense nodes of the cosmic web. So to simulate the small-scale cosmic web, basically I run a tiny box simulation of 0.2 megaparsec with 256 particles. So therefore I can resolve structures down to basically like 1,000 solar mass. And you can see, and this volume is like an average density part of the universe where no interesting thing happens. So this volume will just passively evolve without any dramatic baryonic physics until it gets ionized by external radiation background. So you can see cosmic web structures forming down to redshift of 6 from redshift of 200, where I initialize the simulation. And this is possible because, IGM at this time before reionization has very low temperature, so very low pressure. Then at redshift of 6, I'm going to assume this volume gets ionized externally by radiation coming from galaxies. Turn on some typical intense ionizing background with typical intensity, and basically the gas gets heated and they get destroyed over time, as you expect. So increased pressure, and yeah, all the structures are below the Jeans mass, so basically they cannot exist. But then if you calculate the recombination rate, as in this middle panel, so it starts very high, like much higher, like 30 to 40 times higher than what you expect from the homogeneous gas within the volume because of this cosmic web. And basically, as they get destroyed, the recombination rate goes down. But if you integrate the rate over time, actually you get a significant amount of extra recombination. Basically, extra number of photons you have to spend in order to keep this volume ionized. That's in this case, it's like 0.3 0.3 per hydrogen atom. So, for example, this says that you need 1 photon to ionize this entire volume first time, and then you need extra 0.3 to keep it ionized. And compared to the recombination rate from homogeneous gas without any structure, this is a significant extra. And obviously, this tiny box cannot represent the whole universe, but this is just to show you that this is a significant effect. And also, you can expect this to have some large scale effects because this has very steep time dependence. For example, if you imagine this kind of ionized bubble, you'll have increased recombination rate at the surface because the surface just got ionized, whereas in the inner part, which probably have been ionized for a while, have a much lower recombination rate. So, for example, you can think of having higher recombination rate on average in smaller bubbles because they have higher surface to volume ratio, and also then you can expect this will change the bubble size distribution in your reionization map, and basically that will then propagate to the reionization observables to be measured by future surveys. So obviously this recombination rate can depend on a lot of environmental parameters, and in this recent study I looked into 2 particular physical quantities. One is the baryon dark matter stream velocity, and the other is the X-ray preheating. So if you're not familiar with the stream velocity, but you may be familiar with the baryon acoustic oscillation. It's basically the sound wave in the baryonic component, which didn't exist in the dark matter because dark matter is pressureless. So basically, this acoustic oscillation is also a relative velocity between dark matter and gas. So at recombination, they freeze out, and this is the relative velocity fields between the 2 components, and it's a decaying mode, so it decays as a redshift. During reionization, it's like 1 kilometer at most, 1 kilometer per second at most, which is not strong enough to affect any star-forming galaxies, but they may have a substantial impact on the small-scale structure I showed you. So I looked into that. And also the X-ray preheating, we have unknown number of black holes during reionization, which should emit some level of X-ray background. And X-ray can penetrate deep into the neutral region and preheat the gas. And since the low eigen temperature was the main reason why we were able to form the small-scale structure, probably this will also have some impact on it. So basically, to run simulation with the stream velocity, you have to account for that in the initial condition when you generate initial conditions. And this is done by basically adding extra term in the equation of structure growth for velocity and density. Since the stream velocity fluctuates at very large scale, like 100 megaparsec, because it's a BAO basically, you can assume it's a constant number within the small box that I'm going to be simulating. So in this panel in the left, this is a location in the universe where the stream velocity is very strong, and in the right it's very weak. You can see already the stream velocity is smoothing the gas density field. And the X-ray preheating, I just mimic the effect by raising the temperature floor of the gas particles after H-top 20. So now you're seeing 4 different cases spun by these 2 parameters. And you can see when I increase the stream velocity or increase the minimum temperature, you get less filaments basically, which is expected. So then after that, I basically do the same thing, just expose this volume to ionizing radiation and then calculate the accumulated recombination. And you can see this is like almost factor of 2 effect. So basically this extra recombination from the cosmic wave is now suppressed by a factor of 2 when I either increase the stream velocity level or the X-ray preheating level. Then this has an interesting implication for the large scale reionization, because the stream velocity actually has very large scale fluctuations, 1 degree in the sky at the epoch of reionization. So basically, you can have a 1 degree sized patch of the universe where you need less photons to ionize the universe, whereas in the other patch you need more photons to reionize the universe. So you can expect reionization happening faster in a region with stronger stream velocity. So I did one very simple one-zone calculation where I play with this ionization production model. So this is a black line where the reionization gets inefficient at the end of reionization. And in that case, if I just plug in this recombination rate from my simulation, the end of reionization can be scattered by nearly 0.5, depending on what your stream velocity level is. So of course, this is the most extreme scenario. Typically, I get much less than this. But this is an interesting, in a sense, given this recent observation of quasars by Becker et al., where you find some transmission between ratio of 5.5 to 6, and in the other quasar you have no transmission in the Lyman alpha. And this kind of large-scale fluctuation in the reionization can potentially help explaining this kind of large-scale variation in Lyman alpha opacity. So moving on to part 2, now I'll be talking about these mini halos. So it has been looked into by previous works that these mini halos at the nodes of small-scale cosmic wave, even after the volume is ionized and most of the structures are destroyed, these mini halos can survive for a very, very long time because they have very high density neutral clumps, and it takes a lot of photons to get rid of them. So I was wondering, since they should have very high H alpha column density, maybe they would add a lot of Lyman alpha opacity to Lyman alpha 4S and so on. So I looked into that in this recent study. So to simulate the Lyman alpha 4S, my research group at the LBNL, we have the code called NIX, which can efficiently, very quickly simulate the gas density field needed for the Lyman alpha 4S. So I added some inhomogeneous reionization effect in it. But then this simulation is not able to, simulate the self-shielding in the mini halos and so on. So I have to add that part myself. So this is done by running 1D halo evaporation code by my collaborators. Basically, I start with a spherically symmetric, isothermal sphere, and then I turn on some isotropical ionizing background and basically calculate the evolution of radial neutral column density profile. And you can see even after 500 mega years in this case, still there is very dense core with neutral column density higher than 10 to the 20. So now in this movie, this Lyman alpha 4S movie, as soon as I play this movie, the line of sight is going to hit one of these mini halos right in the center, and you'll get a huge suppression in the flux. Hopefully this will play. Yeah, it plays. Yeah, okay. It's hard to see because it just happened. I'm gonna just move on to the snapshot where this happens. So these blue dots are basically the mini halos that I basically painted using this 1D result. And then this particular blue dot is sitting right on the line of sight, and you're going to hit this in the next snapshot. So after you hit this mini halo, now the flux is suppressed by huge amount, and basically at the end you have a extended gap created by this mini halo. So this is an interesting effect, but this doesn't happen to every sightline. This happens like a few times per gigaparsec. So most of the sightlines, yeah, you won't have this, but occasionally you will see this. So basically extra damped Lyman alpha observers coming from the mini halos. So this is quite preliminary. I also looked into whether they can affect some statistics like 1D flux power spectrum. Seems to be adding mini halos seems to enhance the flux power spectrum at large scale, but it's a tiny effect. But I'm gonna try different scenarios to see whether I'll get any case where this enhancement is bigger or smaller. And next, I also wondered if these mini halos can affect the visibility of Lyman alpha emitters at high redshift, because it's also important tool for studying the reionization. So for that, I used this cosmic dawn 2 simulation run by my collaborators. It's realistic simulation of galaxies at high redshift with the reionization, the ionizing radiation, ionizing the intergalactic medium and so on. So in this map, from left to right, I'm zooming into a brightest galaxy at redshift of 7, and you can see this simulation has very large box, large enough to capture the bubbles and while also resolve the video radius of the galaxy. So I'm basically so these movies are very similar to the Lime Alpha Forest movie I showed you, but except that I start with the double peak emission from the galaxy. And as I go through the IGM, now some part of the emission will be observed. And in these two panels, I'm looking at two different sight lines, only 5 degrees apart. One sight line just avoids this blue dots, basically self-shielded mini halo. And this, in the lower panel, this sight line goes through this mini halo, so picks up basically extra absorption. So in the end, the line strength is 2.5 times weaker because of this mini halo sitting right in the sight line. So I looked into some statistics. So this is basically Lime Alpha visibility scatter plot with and without mini halos for particular galaxies, and I looked into like 10,000 different sight lines. And basically these dots in the upper left are the particular sight lines that are heavily affected by the mini halo. So basically these sight lines, the Lime Alpha visibility is very low just because of the mini halo. So I'll just summarize. Basically, so I looked into this small scale cosmic wave and I found that they can increase the ionizing photon budget for reionization by increasing the recombination rate. And it's interesting in the sense that it can also depend on things like baryon dark matter stream velocity and X-ray preheating, and also the mini halos at the nodes of the cosmic web can add extra Lyman alpha absorption in the Lyman alpha forest and also significantly dim Lyman alpha emitters. Thank you.
I'm not sure if this is a purely semantic question, but what's the difference between your mini halos and a DLA?
So these mini halos will be gone by redshift of like 5 because they all evaporate, but they're like very numerous. So basically, I think these mini halos are going to increase the number density of DLAs significantly over redshift of 5.
So just a lot of caution for this. It's an argument that Martin Hannelt made many years ago. It doesn't belong to me. So all those effects of mini halos depend how fast it happens. So if you just hit one baryon with one photon, it hits the temperature, increases the temperature like as the 10 to the 4. So if you let hydrodynamics do the job, it will just evaporate all the mini halos without any extra combinations. If you do it very fast, you're just hitting the ionizing photons into the wall and they will be consumed. So to do it really properly, one needs to sample all the environments and model the whole history of the ionization, so one knows how fast these different regions with different environments actually photoionize. So it's an extraordinarily difficult problem, actually. So until this is done, all those numbers are kind of shooting in the sky.
Okay, so that was just comment, right? No questions.
That was just a comment.
Another comment. So with James Wadsley, we pointed out how important these were to the Lyman alpha spectrum back in the 90s. And everybody who had done simulations that were about the same time as ours, like Stryker and company, they didn't do it right because they didn't have the resolution. So we had a method to do the resolution. And we found that they were actually very important, but in the high absorption regions. So you would get, the Lyman alpha forest, and then you would get these, and that had been missed. So one comment I would make that was extremely important, in my view, to what we were doing, is that we made effective boxes, which were very large, in order to get the K space. Because what happens, and I've had this discussion with Avishai and others, and as Dimitri and I had pointed out a long time ago, the filaments that exist at high redshift are very different than the filaments now. They're more like thick ribbons, and you have to take that into account to deal properly. So the first simulation you showed was not very big.
Right.
The second one you showed was big enough to be able to get these long wavelength modulations with Ramses.
Oh,
But the first one, this one, was it this one?
this is the small box simulation.
Yeah, the small box. You may find that it's important to put some kind of constraint that larger, you can do it by putting in a shearing field or a tidal field on the box and have it propagate. But you need to take that into account because the tides that are coming from outside of Fourier transform periodic box are actually extremely important to this problem.
Yeah. Actually, definitely. I'm actually working on, first of all, enlarging the box size because obviously 0.2 megaparsec is too small. And it's still, in the large scale universe, we will have a lot of 1 megaparsec boxes with higher overdensity and lower overdensity and so on. So just for completeness, I need to be able to basically explore this parameter space.
Yeah, what you might explore as well is the technique that we used, which we called importance sampling, that we had the probabilities for all of these things that were happening at the different boxes, and then you could put them all together to get the full answer that was K-space correct. So anyway, we'll discuss this more since you're here for a while.
Yeah, sure.
Just this recombination thing interests me. So I just wonder if you've run a simulation without any ionization, with full large-scale structure and small-scale structure and radiative transfer. Maybe that's what you already did. It was unclear to me.
So you mean without reionization? You mean like,
without reionization.
Well, the first step is basically without the simulation without reionization. Where,
okay, so you did do that already.
Yeah.
Because it'd be good to have that as the baseline.
Right.
And understand the physics of this extra effects from structure.
Right.
Before putting in ionization, which makes everything dramatically harder.
Yeah, and this part of the simulation is also interesting in the sense that since there is no interesting binary physics going on, you can be sure that the density field you get is actually quite accurate.
Any other questions? Yeah.
Thanks for the nice talk. I maybe just want to turn Nick's comment into a question and kind of connect the two aspects of your talk. Do you have a sense of this like 1% of sightlines being impacted by these things that are like DLAs? And then you also talked about the streaming velocities changing your opacities by a very large factor. I don't know, any of your slides is fine. But what's kind of the knob that you can change that will make the biggest difference to this?
So this the result I showed you definitely has a lot of uncertainty. First of all, this neutral hydrogen density profile I painted on, it of course depends on the ionizing radiation background I assume, which is highly uncertain. And as you increase it, obviously the halo will evaporate faster, and mini halo gas will be gone earlier. So that has a lot of uncertainty. And also I'm assuming like spherically symmetric isotropy radiation, but in reality you expect the radiation will come from one direction, and then this whole different story. So definitely there are a lot of like steps that you need to make a lot of uncertain assumptions.
Okay, we have time for one more quick question before can the next speaker come in and set up?
Sorry, you probably answered this, but I was not clear where the relative, I know there's a baryon dark matter offset. I just wondered what set the scale for that and the spatial distribution of it.
So
yeah, the streaming field that came from I just wondered, was that your small scale structure, or was that something else?
So this stream velocity field that I showed you is actually a realization from existing code. basically is a baryon acoustic oscillation, so it's well known how to calculate that.
Oh, okay. So
yeah,
okay.
yeah.
Thanks.
All right. Are there any further questions? Well, if not, let's thank. Oh,
there's one on the can you ask on the okay, what is the typical size of mini halos if we want to see their effect in Lyman alpha forest? What's the resolution of the forest?
That's a very good question.
It's
yeah.
from Xiuyan.
So if you go to very small mass, then they will evaporate very quickly, so they will make any difference. If you go to larger and larger mini halos, then the number density will drop. So there is going to be some some mass range that that contributes the most to the Lyman alpha forest, and that depends things like ionizing background radiation and so on. So in this case, I think roughly speaking, between 10 to the 6 and 7 solar mass mini halos are those who can survive long enough and also numerous enough to show up as a GLA as frequently as possible. Yeah.
Okay, let's thank our speaker again.
Thank you.